Hello everyone, I'm Haoting Wei, and today's topic is polylogarithmic approximation algorithm for K-connected direct Steiner tree on Quasi-Bipartite graphs. And the study works with Junxiang, Bandit, and Yu Hao. So here's the overview. The first part, I will give some introduction of our problem and some previous results for the related model. And the second part, I will introduce the high-level idea of our proposed algorithm and some details. So here is an important topic in computer science is that if we want build or construct a network, we will hope this network is strong enough, which means this network can endure some failure conditions, right? So for example, if we want to build a network backbone, we will hope that this network backbone can satisfy some failure conditions so that it can be used more, so that it can be more useful. And so for this kind of problem, we call it as the survivable network problem. So first, if we discuss for the undirected graphs, there are two models. The first is the failure happens on the link or the failure happens on the node. So for the link failure model, there is a two approximation ratio algorithm, and for the node failure model, there is a polylogarithmic approximation ratio algorithm. However, if we try to focus on the directed one, and we say that the directed one is much harder than undirected one. So there are two results for the hardness of the directed one. So the first is that it is at least as hard as the label cover problem. And the second is that for directed one, it's believed that there is no subpolynomial approximation ratio algorithm. And so next, our study focuses on the link failure on the directed graphs, on some special case for link failure on directed graphs. And this problem is so-called K-DST. So what is the K-DST? The definition is that, so given a directly weighted graph GVE, and for each edges, it has a non-negative weight, and there is a root vertex R, and a set of Q terminals capital T, and for each terminals, it has to satisfy some connective requirement K, which is a positive integer. So our goal is try to find a minimum cost subgraph H that has K Edge-Disjoint from root to each terminal's RT path for each terminals. So there is some previous result for the K-DST on the general graphs. So when K is equal to 2, there is a polylogarithmic approximation algorithm and for some gamma shuttle instance. But however, when the K is greater than or equal to 3, there are only a couple of positive results. So the first is that the running time and approximation ratio depends on the structure of the optimal solution. And the second is that there is a by criteria approximation algorithm for the other special case, which is so-called K-GST. The K-GST means the K group standard tree. And so the previous result is for the general graphs, but however, if we want to focus on some special graphs, there's a result is that when k is equal to 1 and the graph is Quasi-Bipartite graph. So the result is log-Q approximation ratio, and this note that this ratio is tight. So what is the Quasi-Bipartite graph? The definition is that, so for any pairs, for any pair of non-terminal vertices, there is no edges between them. So here is the example of Quasi-Bipartite graphs. So in this example, you can see that there is a root vertex R and a set of terminal vertices T1, T2, T3, and T4. And note that in any pair of non-terminal vertices, there is no edges between them. Now, our main result is we propose a polynomial time big O log Q log K approximation ratio algorithm for K-DST on Quasi-Bipartite graphs. And our result also generates the previous result for K equal to 1 on Quasi-Bipartite graphs. So next, for the next session, I will introduce high-level idea about our proposed algorithm. So briefly, our algorithms can be think of as the following three parts. The first part is that since we have to find some subgraph and which is minimum cost, and for each terminal vertex, it has k Edge-Disjoint paths, right? So actually, the first step is that the so-called rooted connectivity augmentation, briefly, is that in each round we will add one connectivity for the new form graph. Then finally, at most k round, our solution will become a k connected, right? But so the second step is that in each round, we know we want to increase one connectivity, and we will use the other technique, which is called hollow set decomposition, and we also define this problem as the covering hollow families, which means we have to find some edges to cover some subset of nerded, which is called hollow families. But the problem is that how can we solve this problem covering hollow families? We will reduce to the set cover. And if we look it as a black box, then we can use the set cover ratio and combine the above two steps ratio, then it will give us an efficient approximation ratio algorithm. So first, I will introduce the highest level of our proposed algorithm is the rooted connectivity augmentation. So actually, the idea of rooted connectivity augmentation is very simple. Is that in each round we just find some edges, then the new form graph will increase at least one connectivity for each terminal vertices. So in this example, if the initial graph H0 is an empty graph, then in this round we will try to find some edges, then H1 will become one connected graphs. So next, I will introduce some useful notations which will be used in the following paragraphs. So the first is the difference set. So if the current graph is I-connected, which means for every terminal, there are Edge-Disjoint paths from root to this terminal vertex. Then the definition of the difference set is that is a subset of vertex which contains some terminal vertex, and it needs one more edges to become I+1 edge-disjoint paths. So if we want to remove this different set, which means we will add some edges, then this different set will have I+1 edge-disjoint paths, right? After adding this edge. So we also say that this edge E covers a different set. If we add this edge E, then this different set has I+1 edge-disjoint paths. So the next is core. Actually, a core is also a different set, but it has a property that there is no different set can contain in this core. So finally, the next ones are hollow families and hollow sets. So both hollow families and hollow sets are related to some core C. So the hollow family of core C is the collection of all different sets that contain this core C. And the hollow set of some core C is the union of all the different sets in some hollow families. So here is a simple example for the different set cores, hollow families, and hollow sets. So for it, for I is equal to 1, which means that so for I is equal to 1, we can see that the core is this terminal vertex T1, since core is also different set, and different set has to contain some terminal vertex. So the core is this terminal vertex T1. And for the hollow families, relating this core, it contains two different sets, T1, and the other different set content is T1V2. And the definition of the hollow set is the union of all of the different sets in this hollow family, so that the hollow set will equal to T1V2. So here is the figure to show that if we add some edges, then there is another edge-disjoint path from rooted to this different set, then we can remove this different set. So on the left-hand side, this is a different set when, for the case I equal to 1. And if we can find some edges, then it will form another edge-disjoint path from root to this different set. Then we can remove this different set. So we know that for the rooted augmentation is to find some edges and increase one connectivity in each rounds. But how can we achieve this result? So we will use some technique which is called hollow set decomposition. The idea is that we can decompose the current graph into different hollow set, and this time is polynomial. So in this example, you can see that if we apply the hollow set decomposition, there are two hollow sets which is related to core C1, C2, C3, and C4. So next step is that we have to find some edges to cover all of the different sets of these hollow families, so that if we can remove all of the different sets into these hollow families, we can argue that we have augment 1 connectivity, right? So actually in each round, our algorithm cover hollow families very greatly. So, but this problem is that because for a hollow set decomposition, it only we cannot some cores will not appear in the hollow set decomposition. So for this figure is that if we use the HE1 to cover some core C1, and we use the HE2 to cover some core C2, at this time, there will be a new core C3 appear. But however, we have covered these two old cores already, so that the number of cores will be decreased by a constant factor. So, which also implies we can cover all of the hollow families within big O log Q iterations, right? So that this is the factor of the big O log Q. So here's another example for covering hollow families. So in this example, the hollow families contain 3 different sets, U1, U2, and U3. And note that the U1 is the core. So in this example, we can use the set of edges E2, E3, E4 to cover these hollow families. Or we can also use E1, E4, E5 to cover these hollow families. And this example also point out an important some key point is that in this example we can see that so no matter which edge set, we have to use one edge which is from the outside to go into this hollow families, and a set of edges inside these hollow families, right? So actually we call this kind of edge E1 or E2 as the incoming edges, and the edges E3, E4, E5 as inside edges, which means the edges, both end of these edges is inside these hollow families. So we have known that the problem covering hollow families is to find a set of edges to remove all of the different sets, right? But how should we choose this set of edges? So here we observe that we can reduce to the set cover problem or the facility location problem, since we have to use an edge into hollow families and a set of edges inside the hollow families. So, if we look this procedure as a black box, then which means we can apply the approximation ratio of the set cover problem directly, which implies another log Q factor, right? But we note that if we think of this step as the white box, we can combine these 2 steps just into 1 step, so that we can improve big O log Q factor, and the detail is presented in our paper. So here is the example of why this reduction is valid, because we can use an important property of the quasi-bipartite graph, which is called internal Edge-Disjoint, which means that for every edge is unique for some hollow families. So actually in this example, you can see that this edges UV can be used as incoming edges for a hollow family which related to the core C prime, and an inside edge for the hollow family C for this core C. And because the internal edge disjoint property. This edge will be the unique inside edge for some hollow family. So that for every edges, it will be used at most twice at the same time. So finally, here is the summary of our study. Is that actually for this problem, we try to decompose it into 3 steps. The first step is the rooted connectivity augmentation, and which means that in each round we add one connectivity. We add one connectivity. Then, so how can we add this one connectivity? We will use the hollow set decomposition, then try to find some edges to remove all of the different sets. And we also call this problem as cover hollow families. And the next step is that it's about how to choose this set of edges. Then we reduce this problem to the set cover problem so that we can look it as a black box, so that which implies a non-local factor. But yeah, but as the previous pages that I mentioned is that we actually we can combine these 2 steps just into 1 step, but it have to use more complicated skill and analysis. So the detail is presented in our paper. So thank you for your listening. Hope you enjoy our talk. Thank you.